Hello, math learners! Our lesson for today is about the graph of logarithmic function. The learning objectives are: you are going to recall exponential function, sketch the graph of logarithmic function and its inverse, and graph vertical and horizontal shifts of logarithmic function. Let us have some important notes. Logarithmic function is the inverse of an exponential function. Remember that the inverse of a function is obtained by switching the x and y coordinates, and this reflects the graph about the identical line y is equal to x. The logarithmic curve is a reflection of the exponential curve. The table here demonstrates how the x and y values of the points on the exponential curve can be switched to find the coordinates of the points on the logarithmic curve. The given exponential function is f of x is equal to 2 raised to x. And the given logarithmic function is y is equal to the log of x to the base 2. And here are the points on the exponential curve. We have the point with coordinates -2 and 0.25. And the point with coordinates -1, 0.5. Then we have the point with coordinates 0, 1, then 1 and 2, and the point with coordinates 2, 4. For the points on the logarithmic curve, we have 0.25 and -2. We simply interchange or switch the values of the coordinates. So from -2, it becomes 0.25. And from 0.25, it becomes now -2. So the next point on the logarithmic curve, we have 0.5 and -1. Next, a point with coordinates 1, 0. Next, a point with coordinates 2, 1. And then a point with coordinates 4, 2. Looking at the graph, the blue one is the graph of the exponential function f of x is equal to 2 raised to x. The green dotted line is the identity line y is equal to x. The red curve is the graph of the logarithmic function. As you can see in the graph, the logarithmic function is just simply the inverse of the exponential function. So here, the red one is the mirror image of the blue curve. Next, let us determine the value of y given y is equal to the log of x to the base 2. So with these points of the exponential curve, we have the points here on the logarithmic curve. So to find the values of y here, how to get the -2, so all you have to do is to replace x by 0.25. The given value of x is 0.25. So what you will do is to substitute 0.25 to x, and then you can take the log of 0.25 over the log 2 by applying the change of base formula, and the result is y is equal to -2. Or simply, you can use your calculator. Just press log 0.25 to the base 2 and it will give you -2. That is why we have here y is equal to -2. For the other solutions, you can do it yourself. Let us compare the properties of exponential function with the properties of logarithmic function. So consider the table at the right. For the exponential function, given the standard form y is equal to a raised to x, wherein a is greater than 0 and a is not equal to 1. For the logarithmic function, we have y is equal to log x to the base a, where a is greater than 0 and a is not equal to 1. So for example, the exponential function is y is equal to 2 raised to x. And the logarithmic function is y is equal to the log x base 2. The domain for exponential, we have the set of x such that x is an element of real number. For the domain of the logarithmic function, we have the set of x such that x is greater than 0. For the range of exponential, we have the set of y such that y is greater than 0. And for the range of logarithmic function, we have y such that y is an element of real number. There is no x-intercept for exponential. For logarithmic, the x-intercept is equal to 1. This is also the value of the 0 of the function. For the y-intercept, y is equal to 1 for exponential, and for logarithmic, it is none. And the trend is increasing since 2 is greater than 1. And also with the logarithmic function, there is no vertical asymptote for exponential, but for logarithmic, we have y-axis, or the line x is equal to 0. For the horizontal asymptote, for exponential, we have x-axis, or y is equal to 0, and none for logarithmic function. And the graph is continuous for exponential as well as for logarithmic. And the form of the curve is, for exponential, it is concave up, while for logarithmic, it's concave down. Take note, a graph is said to be concave up in this form at a point if the tangent line to the graph at that point lies below the graph in the vicinity of the point. So, supposing this blue line is the tangent line, it is placed below the curve. And concave down at a point if the tangent line lies above the graph in the vicinity of the point, as shown in this figure. So this is the tangent line and it is placed above the curve. The graph is increasing if a is greater than 1, and the curve is concave down. And the graph is decreasing if a is between 0 and 1, and the curve is concave up. Let us have now the steps in sketching the graph of logarithmic function. The first is you have to graph the identity line. The second step, we have to graph the exponential function. The third one, we have to graph the logarithmic function. Then we have to give the properties of the graph of logarithmic function. And do not forget to label the graph completely. Let us have an example. Supposing you are asked to sketch the graph of g of x, which is equal to the log of x to the base 2, or it can be written as y is equal to the log of x to the base 2. First, you have to construct the table of values of the identity line y is equal to x. So, if the given values of y are negative 1, 0, 1, 2, and 3, then the values of y are identical to the values of x. So we have y is equal to negative 1, 0, 1, 2, and 3. Then, we have to plot the points in the Cartesian plane. So the first point with coordinates -1 and -1, then followed by 0, 0, 1, 1, 2, 2, 3, 3. Then after that, you have to connect the points with a dotted line. And you have to take note the coordinates of the points are just simply identical. So let us have now the graph. It's plot -1, -1, 0, 0, 1, 1, 2, 2, and 3, 3. And then connect with a dotted line. So this is the graph of y is equal to x. For step 2, you have to graph the exponential function f of x is equal to 2 raised to x. First, we have to construct the table of values of the exponential function. So, assigning values to x, we have -2, -1, 0, 1, and 2. For the values of y, we have 0.25, 0.5, 1, 2, and 4. So I'll be giving you only one example on how to get the value of y. At x is equal to -2, so all you have to do is to replace x by a -2. So we have now 2 raised to -2. And this can be simplified into 1 over 2 squared based on the laws of negative exponent. And then this can be simplified into 1/4. And you can change 1/4 into decimal, which is 0.25. So the value of y is 0.25. So it's here. So for the other solutions, you can do it yourself. Then afterwards, you have to plot the points in the Cartesian plane. And then you have to connect the points with a curve. Let us have now the graph of the exponential function. Let us plot now the points in the Cartesian plane. So we have first point here, here, next here, next, and the last point with coordinates 2, 4, and then connect with a curve. For step 3, you have to graph the logarithmic function g of x is equal to log x to the base 2. So first, you have to construct the table of values of g of x is equal to log x to the base 2. So the assigned values, we have 0.25, 0.5, 1, 2, and 4. And for the values of y, we have -2, -1, 0, 1, and 2. Or simply, we just interchange the x and y values in step 2. So you have to plot the points in the Cartesian plane. And these are the coordinates of the points. So let us plot now the points. We have the first point there, second red point, and the last red point. Then connect the red points with a curved line. So again, you can use the table of values in step 2 and switch all values of x and y. Step 4, you have to give the properties of the logarithmic function. So for the domain, as you can see, you have x such that x is greater than 0. So starting here, you cannot use x is equal to 0 because this is the vertical asymptote. You can use only greater than 0. Then for the range, we have y such that y is an element of real numbers. Meaning you can use all the values of y. For the x-intercept, it is x is equal to 1 at 1, 0. So if you notice in the graph, it crosses this point with coordinates 1, 0. So this is the x-intercept. For the vertical asymptote, it is the y-axis, or this is called x is equal to 0. Meaning the graph of the logarithmic function will not cross the y-axis. The graph is continuous and the graph is concave down. Aside from looking at the graph, you can also identify the x-intercept by using this solution. So we have g of x is equal to log x to the base 2. Or you can change g of x into y equals to log x to the base 2. And since we're solving for the x-intercept or the 0 of the function, we change y into 0. Then after this, we are going to change the logarithmic form into exponential form. So the exponential form is 2 raised to 0 is equal to x. And the value of 2 with exponent 0 is 1. That is why the value of x is equal to 1. And do not forget to label the graph completely. So label it with the coordinates, with the name of the function here for the logarithmic function. And this is the identity line. And if possible, you can use different colors to distinguish one function from another function. Do you have questions? If there is none, let's recap on how to sketch the graph of the logarithmic function given y is equal to log x to the base 2. So for step 1, you have to graph the identity line y is equal to x. Using the table of values, then we can have these points in the Cartesian plane. And then later on, you connect with a dotted line. Step 2, you have to graph the exponential function f of x is equal to 2 raised to x. And this is our table of values. So let us plot the points now in the Cartesian plane. So we have here the point, another point, another point, another point, and the last point with coordinates 2, 4, and connect. Step 3, you have to graph the logarithmic function g of x is equal to log x base 2. And this is our table of values. So we have to plot now the points in the Cartesian plane. So the first point is here, second point, third, fourth point, the fifth point, and we have to connect the points with a curve. And then afterwards, we have to give the properties. So these are the properties of the logarithmic function. And then we have to label the graph completely. Do you have questions? If there is none, let's proceed. Let us have now graphing a horizontal shift of g of x is equal to log of x to the base b. When a constant c is added to the input of the parent function, which is g of x is equal to log x to the base b, the result is a horizontal shift c units in the opposite direction of the sign on c. To visualize horizontal shifts where c is equal to 3, let us observe the graph of the parent function of g of x is equal to log x base 2 alongside the shift left, which is h of x is equal to the log of x plus 3 to the base 2, and the shift right I of x is equal to the log of the quantity x minus 3 to the base 2, where c is greater than 0. If we have to shift left, the given function is represented by h of x is equal to the log of the quantity x plus 3 to the base 2. So this red one is the parent function, or the original function g of x is equal to log x to the base 2. So if it is positive 3, so you have to move 3 units to the left. So from here, 1, 2, 3. So it's 3 units. And from the vertical asymptote, you have to move also 3 units. So meaning the vertical asymptote changes to x is equal to negative 3. The original, that is x is equal to 0. For the domain, it changes to negative 3 to positive infinity, or the domain now is greater than negative 3. In the original function, the domain is greater than 0. By this time, if we have the shift left, the domain becomes greater than negative 3 because the vertical asymptote is line x is equal to negative 3. And for the range, it remains the same. It is still y such that y is an element of real numbers. So you can still use all the values of y. For the shift right, represented by I of x is equal to log of the quantity x minus 3 to the base 2. So you have to take the opposite direction when it is x minus 3. You have to move to the right 3 units. From here, it's 1, 2, 3. The point now is here. And the vertical asymptote is also moved 3 units to the right. And we have now the vertical asymptote equivalent to line x is equal to 3. So the vertical asymptote changes to x equals 3. The domain changes to x greater than 3. And for the range, remains the same. Still y element of real number. So here, from here to here, that is equivalent to 3 units. From here to this point, it's 3 units. And also from this vertical asymptote to this one, it's 3 units. From here to this vertical asymptote, it is also 3 units. And if you would like to make a table for the shift left, h of x is equal to log of the quantity x plus 3 to the base 2, the vertical asymptote is x is equal to negative 3. So let us plot this in the Cartesian plane. So for the vertical asymptote, then the first point, the coordinates negative 2, 0, negative 1, 1, 1, 2. Then you have 5, 3. And then connect. And then for the shift right, represented by I of x is equal to the log of the quantity x minus 3 to the base 2. Then the vertical asymptote is x is equal to 3. And we have the table of values. Let us plot the points now in the Cartesian plane. So we have the vertical asymptote, x equals 3, first point. Then the next point. Then we have the third point and the fourth point, and connect with a slight curve. Still, as you can see, from the original 1, 0, you move still 3 units to the right to represent the I of x function. And you move 3 units to the left to represent the h of x function. Questions? If there is none, let's proceed. Let us have graphing a vertical shift of g of x is equal to log of x to the base b. When a constant d is added to the parent function, which is g of x is equal to the log of x base 2, the result is a vertical shift d units in the direction of the sign of d. To visualize vertical shifts where d is equal to 3, let us observe the graph of the parent function, which is the g of x, alongside shift up for h of x is equal to the log of x to the base 2 plus 3. And shift down, I of x is equal to the log of x to the base 2 minus 3. So for the shift up, the vertical asymptote remains the same. So it is still line x is equal to 0 or the y-axis. The domain remains the same. We still have x greater than 0 because the vertical asymptote is 0. So we will use greater than 0. The range remains the same. It is still y, element of real number. So you can use all the values of y. And then for the shift down, this blue one represented by I of x, the vertical asymptote remains x is equal to 0. So it is still the y-axis. The domain remains x greater than 0. And the range remains the same. It is still y, element of real number. So for h of x is equal to log x base 2 plus 3, all you have to do is just simply move 3 units up. 1, 2, 3. And for I of x is equal to log x base 2 minus 3, just simply move 3 units down. So that is how to do the vertical shift of the logarithmic function. And we can also assign values. This is the parent function or the original function, which is the g of x. So for the shift up, represented by h of x, we can have the vertical asymptote the same, and we can use this table of values. So let us plot now the points in the Cartesian plane and connect with a curved line. And for the shift down, represented by I of x, which is the log of x base 2 minus 3, the vertical asymptote is still the same, and we can use this table of values. Then plotting the points in the Cartesian plane, we can have this point, this one, and the last point, and then connect with a curved line. So, do you have questions? If there is none, then see you next time. Bye!